Hi, I'm Vaibhav Unhelkar. I'm a faculty of computer science at Rice University. In today's talk, I'll be talking about joint work done at MIT with Shen and Professor Julie Shah on decision making for human-robot communication. In our work, we are interested in designing collaborative robots, such as this one, for supporting humans in sequential tasks. Examples of such sequential tasks exist in manufacturing, healthcare, space, and even our homes. For example, consider this human and robot team working together to make meals. The human is making sandwiches while the robot is pouring drinks into cups at the same shared table. Here, the human and robot need to coordinate their activities for completing the task efficiently, that is, as soon as possible, and safely, that is, without collisions. For instance, while the human is working at 2, the robot is prevented from going there, and the robot can use prediction and planning capabilities to improve the safety and efficiency of the task. To formalize such tasks of interest, we use the factor to agent MDP model. The choice of this model is motivated by prior art, and here we describe our task with this MDP. The state of this MDP describes the features that are important to describe the task. For example, the position of the human, the joint angles of the robot, as well as the progress of the task. The action describes the joint action, that is action of both the human and the robot. In this example, this would correspond to task and motion primitives for each of the agents. The transition model corresponds to the physics of the world as well as the rules of the task, and the shared objective describes what does the team need to achieve. For instance, in this task, safety is emphasized by prescribing a negative penalty for collisions, and efficiency is prescribed by providing a positive reward for task completion. These tasks can grow significantly large in terms of their state space. For instance, in our implementation, this task had more than 10,000 states, and the robot had to reason about these states in a short planning time. Our goal is to design effective policies for such robot teammates by anticipating human behavior, selecting robot actions, and also leveraging communications. Communication can be critical in designing effective teammates. As such, there has been significant effort, both existing and ongoing, on developing robot communication modalities. These modalities answer the question, how should a robot communicate? But an equally important question is if, when, and what to communicate. This question has been addressed in multi-robot and multi-agent communities, but has received limited attention for human-robot teamwork. The reason this question is important is because if the communication is less or too much, the performance of the human-robot team may suffer. The contribution of our work is CommPlan, a new framework for generating joint action and communication policy of a collaborative robot. CommPlan answers the questions if, when, and what to communicate for a robot, given specification of the task as an MDP, data of humans' behavior, and a library of robots' communications, that is a communication modality. In order to incorporate communication in our task model, we add additional actions for each of these agents. These actions do not change the state of the environment directly, but allow both robot and human to communicate with each other. In order to keep our framework modality agnostic, we reason about these communications in terms of types rather than how they are actually implemented. We consider 4 types: inform, ask, command, and answer. These can be implemented through multiple modalities or different modalities. In our implementation, this was done using speech. Given these tasks and communications, the question that we need to mathematically answer is how should the robot choose its actions and communications? These actions and communications based on prior art should definitely be chosen based on the state of the task, but also on the actions of the human, that is behavior of the human, and the mental state, that is X of the human. The latent or mental state of the human is equally important while designing robot behavior. In our task, this corresponds to the intent or goal of the human, that is which location is the human going to go to next. Since the robot cannot observe this, the robot has to make decisions in a partially observable sense, and we utilize a POMDP-based framework to do so. Specifically, we build upon AdaCoRL, a POMDP-based framework for generating action policy of a collaborative robot. CommPlan and AdaCoRL share several similarities. They consider latent states, they learn human behavior from data as an AMM, and they plan robot behavior using POMDPs. For more details on AdaCoRL, I refer you to our paper in Coral last year. But AdaCoRL has a limitation. It can plan for robots' action, but not for its communications. CommPlan fills this gap. It includes mechanism to gauge costs and to gauge the cost and benefits of communications. To do so, it includes first a cost model of the available communication types. This cost model depends on both the communication type and modality, as well as the time since last communication, and allows us to model the fact that some communications are more costly than others, and even the same communication can be more costly if it is unnecessarily repeated. The communication cost, task objective, and human behavior are then used to define the reward of the robot model. The human response model captures how human responds to the robot's communication. For example, does the human change his or her behavior based on the robot's communication, or how does the human respond to the robot's communication? This model helps us define that different human responds to different types of communications differently. This is incorporated in the transition and observation model of the POMDP, so that CommPlan can jointly reason about robots' actions and communications. To get more detail on how this is done mathematically, I encourage you to read our paper in this, on CommPlan. We implement CommPlan on the example that we have been using, on the task that we have been using as the running example. Here, the robot needs to share the space safely and efficiently, to just reiterate, with the human by effectively choosing both its actions and communications.
Please make the next sandwich at 2.
This video demonstrates how CommPlan works in action. The robot can choose its actions and communications throughout the task. Here, the robot could choose to communicate at any point, but it chooses to do that at the start of the task because it did not know where the human would go. By disambiguating where the human should go, the robot was able to do the task as well as the human was able to do the task safely and efficiently. Now, the robot does not communicate while choosing its next action because it's not necessary to do so. It has a good model of where the human is going to go next, where the human is going to be next. For a complete video, I refer you to the supplementary material available with the paper. We also quantitatively compare how CommPlan fares with some baselines. First, we compare it with a no communication policy, where the robot's decision was still made with a latent state based model, that is with a POMDP defined by AdaCoRL, but the robot was not communicating. We hypothesize that in absence of communication, AdaCoRL will perform poorly as compared to CommPlan. We also compare it with a handcrafted communication policy, where the action decisions were made with AdaCoRL, but a handcrafted policy was used for communications. Encouragingly, we observe that CommPlan performs statistically significantly better in human subject experiments as compared to both the baselines. This shows that by jointly planning action and communication, CommPlan can result in effective human-robot collaboration. What was more interesting is, despite similar number of communications, the handcrafted policy did not perform as well as CommPlan. And this shows that CommPlan can not only communicate, but communicate effectively, use those communications effectively to improve the team's reward. In summary, the contribution of our work has been a novel framework for generating joint action and communication policy of a robot. I encourage you to use this framework, especially if you have a task in mind and you have a robot that can communicate, but you want to answer the question if, when, and what to communicate. We have implemented this framework, as you saw, with speech as the communication modality, but we are equally excited to explore extensions of this work with other modalities such as vision, motion, and visual signals. Thank you.